who is going to tell us about whether we can trust our encrypted cloud services or not.
Yes, that's exactly what I'm going to talk about. So this is something I did some time ago, and I did it with my current advisor. So I work at Aarhus University, and I do like cryptography daily. So not so much security, but like cryptography. And this is like, there's a lot of cryptography in this. Okay, so can you trust your encrypted cloud? This is an assessment of like one of these applications that you can use. So to put like this into some context, it might make sense to like, what do I think of as like a traditional cloud storage? So when I say traditional cloud storage, I'm thinking something like Google Drive or Dropbox or something like this. And these applications, like the traditional cloud storage, you know, where you just put your file on some server and now it's there, it's nice because now you can access it even if your computer gets stolen and so on, but it still raises some concerns with regards to the privacy of your file. So for example, like besides myself, who else can read this file? And of course, you know, anyone with access to these servers will be able to read the files. There are some more like subtle issues. For example, if we delete a file, I store a file on like Google servers, now I delete it, is it actually gone? Do I have like any assurance that somebody who later comes along, I don't know, steals Google servers or the NSA, I don't know, takes control of these servers, do I actually have a guarantee that they can't, you know, recover my file? And I don't really have this. And the same applies, of course, with if I cancel my account or something. There was an incident like a couple of years ago with Dropbox where they got into some trouble because they suddenly started to basically recreate files that people had deleted up to like 6 years ago or so. So that's not really like, even if I delete this file and it's completely gone from my account, suddenly it shows up again because it's actually not deleted from the servers, right? It's, yeah. And of course, what happens if, you know, this storage company is sold? I might trust Google or I might trust Dropbox or whatever, but what if it's suddenly sold to some, you know, I don't know, Chinese company or company that I don't trust, right? It's the same problem again. It's because I don't have control over my files anymore. These storage systems, these encrypted storage systems, they solve this in like the most simplest way you can think of. Like you have a password that you use in any event when you log in. So now you just use this as well to somehow derive a key and then you encrypt this password and then you upload it to the server. There's a lot of like caveats here because now you can't use the proper authentication anymore, and this is some of the things that we exploited in this thing. But like this is basically the idea of all of these encrypted cloud storage applications. They do basically this. Of course, like in real life, it's not just, you know, it's not so simple that you just derive a key from your password and use it to encrypt your files, because, you know, an application should perhaps do a bit more than just, you know, encrypt the file and put it on the storage device. You also want it to be able to, well, authenticate first of all, because some of these applications, they might have like additional data. There is some information associated with you, so they can contact you. There might be some payment involved and so on. You want to be able to get like your files on both your laptop and your phone, so there's some synchronization of files. You might want to be able to say, I want to share this file, and so on. So there's like a lot of details here that add like complexity on top of this, but in a nutshell, this is basically what happens when you use these services. They encrypt your file with your password. So the idea of these is essentially to protect it. So I think the best way to see the security they want to achieve these services is they want to protect like your files against the server themselves, right? Because you're storing the files on the server, but you don't trust the server to actually, you know, not read the files or not suddenly, you know, lose them or something like this. So you essentially want to protect them against the servers. And this is essentially what they claim, all of these. So I have some quotes from like these companies. It's like, you should never have to trust a cloud storage server, or LastPass, which is essentially also encrypted cloud storage, but now of like short strings, which is your passwords, I guess, say the same thing. Sync is another program that does this. SpiderOak says also this, like no knowledge means we know nothing about the encrypted data you store on our servers. So basically, you want to protect your files against the server in some way. And what we actually look at is like, to what extent are these claims actually true? So all of these are, of course, you know, taken from when you go to the web page, this is, you know, in big text on the front page, so they can sell their product and so on. But is it actually true? Like, or to which extent is this true? So the way we went about this is that we first like defined some sort of like threat model for this. So when they say, you know, you don't have to trust the server, what do they actually mean by this? Because you can interpret this, you know, you shouldn't have to trust a cloud storage service. You can interpret this in a lot of different ways. And depending on how you interpret it, some of them are secure, like at least like the SpiderOak we looked at, it might be secure, it might not, depending on how you interpret, you know, the can I trust the server, for example. Then we did like a bunch of reverse engineering of this application in order to see if it actually worked. And then we found out that it was not secure, and then we like wrote a bunch of proof of concept code, and then we executed these attacks, and then we, you know, sent them an email and they fixed their stuff and so on. So everything is like back to the status quo, or whatever you might say. Yeah, so like a small like note here that, of course, cloud storage, since I'm like doing research daily, I don't know, I have to plug some research that is, you know, being done on cloud storage. Of course, it's not just like, as was mentioned in the previous talk, and it's the same here, it's not just like homemade crypto everything, there's also like some research involved in this, but yeah. Okay, so very informally, we consider this setting where you have like a client and server, so we don't really care about like many clients and or a setting where the client has like a lot of devices and so on. We take like the simplest possible case where you say, I have a client and I have a server, and the client basically wants to store stuff on the server, and the server wants to, I don't know, give this stuff back to the client, but we somehow, you know, cannot trust the server completely. Because if we could trust the server completely, obviously what we would just do is that we would just send the files to the server, right? We might use TLS or something so everybody else cannot read what we're sending, but if we trust the server, then there's no point in encrypting our data, right? Because we trust the server. So we consider basically two cases. So either we say that we are against, like, we ask like, is it secure if this server is like only passively malicious? Which basically means we trust the server to do everything that it's supposed to do, but we don't trust it to not try to read our files, right? So it essentially says that, you know, if everything works normally, then stuff shouldn't break. Like this should be like the minimal requirement, right? This you might see that, for example, something like a Gmail account, for example, would not be secure against this, clearly, right? Because everything, of course, works and so on, but just because you're like storing your emails in like clear text on Google servers, of course, they can know the content of your emails. But it's, of course, not really the, you know, the goal of Google to like hide the content of your emails, because they use them for various things, right? So this is for something that where you cannot trust the server in some sense, this should be like the minimum, right? I cannot trust that, like I trust the server to do everything correctly, but I don't trust it to not read my files. That's basically it. This is in some sense, it also provides security in the case where you say, okay, I actually trust the server to do everything correctly, but I don't trust them to, you know, not get hacked, for example. Right? So if your files are secure in this case, then it's also secure if somebody breaks into the server and even learns all the server's, you know, database, like encryption keys and so on. That's like the most, you know, the most a company can lose the data, right? If it loses everything, then it would still be fine in this case, because the server cannot read the files. Obviously, anybody who breaks into the server also cannot read the files. So it's not just if you don't trust the server, it also has like nice things outside of this. The other thing is like, what if like the server just does whatever it wants? So like I say I want my files back, and now the server just sends me whatever, you know, it can send me whatever it wants. This is perhaps a bit less realistic, because in practice you'd imagine, you know, this is, you might, you know, see if this happens, right, from the server. It's a lot more fun to study, of course, but it's also worth like considering, because it might be the case that, I don't know, you could probably come up with some I don't know, strange scenario, right, where the server is like taken over by some hacker or an intelligence agency, and they target a specific user. And now against this specific user, the server sends like specific messages in order to try to break basically its own application, right? And this is essentially what we have here. Of course, there's like a small note here that we test this we test these two threat models against like software we get from the server itself, essentially. So in particular, like in the second case here, you might argue, obviously no cloud storage application where you get the application from the cloud storage servers is secure here, right? Because what the server just does in this case is that when you ask it for the software, it just, sends you broken software, basically. That just reveals your files as soon as you start using it. So there's like a small asterisk here saying that we consider this in the case where you already have, the right software, so to speak. So like the software you get from the server, and the server does like its best with this software. So this is basically saying you have the software before, and now can the server somehow abuse bugs or protocol flaws or something in its own software to somehow break the security of what you have. Whereas I guess the other one here you can say is like, is it just broken from like without doing anything? Okay. I guess, no, this is not really that interesting if you don't like cryptography, I suppose. We also provide like a simple formal modeling of what this means, these two things. And essentially what you would do is that you set it up as like a game. You make some assumptions about how the user picks his password. In this case, you assume that he picks his password as something which has kappa bits, and he picks it at random, which is not, of course, true in real life, but it suffices for a formal modeling. And then you play like a small game, and it's like the rules are very simple. Like the adversary, he can ask the user to upload two files. One of these files are encrypted, and the server, like the guy who attacking the system, he wins if he knows which of these files was actually encrypted. So this is like the most, I guess, pessimistic situation where the guy who's attacking you knows everything about what you're storing, except which files you're, like, of these files you're storing. So basically, he gives you two files. It might just be a file with, like, in one of them there's like a 1, in one of them there's a 0, and now you upload one of them. You don't tell the guy which one you upload, and you just upload one of them. And now it's secure if he doesn't know which one of these you actually stored. So even if he knows which files you're actually storing, as long as there's still some like uncertainty. And that's basically what this is, but it's not like super important. I just included it here. Okay. So everything based on the passwords, we make like 3 categorizations of what an attack can be in this case. Like one of them is like, okay, you recover the user's password and remember that everything in the end is like encrypted with the user's password in some way. So you cover the user's password like it's game over, right? Now you can decrypt everything because the attacker here is still the server, so he has all the encrypted information and so on. So there's nothing else besides the password essentially. All right. It might be the case that he can recover like one file without actually knowing the password. And you see, like, we'll see how this could be in this case, because it's not clear from the simple situation before, or it might actually be because you might leak some derivation of the password, but not the password itself. So this doesn't reveal the password, but it does reveal enough information to actually recover the file. The last thing, it might be possible that you somehow run a protocol that just basically weakens whatever information you have about the password beforehand. So typically the way these protocols, or like, sorry, these applications perform authentication is they derive, like they hash the password basically using a strong hash function, or like a key derivation function. And it might be the case that you can actually tweak this from the servers. So now instead of getting a good derivation of your password, you get like a weak derivation that can actually be brute forced. That's essentially what you have down here. You like weaken the security by some factor, Greek letter. Yes. Okay. So some information about this application. So as mentioned again, it's a bit more complex, but what is essentially happens in SpiderOak is that you have the password. You use this somehow to encrypt like some long-term keys. These long-term keys are used somehow to encrypt directory keys, so you get like a key for each directory, and these are used to encrypt files. So you get like this nice kind of like hierarchy of keys. Like in the end, from the server's point of view, only this guy up here is unknown. Like he has everything else, which is of course encrypted, but in the end he only needs to know this guy in order to reveal everything down here. Communication is fairly simple. It's like some back and forth to do authentication, and like this is actually the most interesting part, the authentication, because typical password over TLS authentication doesn't work anymore. So when you log into like any online service, essentially what happens is that you send your password and your username to the server. The server does something to check that this was the right combination of username password, and now it lets you in based on this. Obviously, this doesn't work anymore if you cannot give the password to the server, right? So what they do instead is, instead of using any of the protocols that has been developed within the last 25 years on like authentication that doesn't reveal the password, they designed like a couple of their own, which of course doesn't work. So once you have authenticated to the servers, then everything is basically RPC using something from the Matrix library. So this is like a Python framework for network communication. And I know there's a bunch of extra stuff in a typical cloud storage application, but this application had something like 95, I think, different methods that the server can call on the client, which is like a lot. And we also found out that this can also be abused in like very, very silly ways, essentially, to break the security totally. Okay, so briefly about encryption. So basically, like, how does this this stick figure to the right, what does this work? So when you want to encrypt something in this application, you take the password, an ID, your file, you generate some random keys, in this case like one for the file, one for the directory. You derive a key based on the password, so using a key derivation function. This is, in practice, this would be pbkdf2 with some fixed parameters. So basically just hashing this 10,000 times. That's essentially what happens here. You encrypt the file using this KF, which is a random key. You encrypt this KF with this KD, which is another random key, and now you encrypt this KD with the key from your password. So this is basically what happens here, right? You have you can imagine you have the file down here somewhere, and now you have this key encrypted with this key, encrypted with some key up here, encrypted with this one. So that's how, like, this is how it works, more or less. The reason for doing this is that you can imagine this basically as putting the key in a header of the file in this way. It gives some flexibility. In particular, if you want to share a file, it's enough to just send this key to whoever, plus of course the ciphertext to whoever you want to share this with. And if you want to share like an entire directory, it's also just a matter of sending like one key. And we imagine that this is this is at least some of the reason why they pick this particular scheme. It's because it makes file sharing very efficient. Of course, note, security is entirely dependent on the password. Okay. The entire thing is written in Python. This is great, because Python is very easy to decompile. Well, you can apply obfuscation to this. I know this is something that happens in Dropbox. They obfuscate their applications. But SpiderOak doesn't. So you can take like any off-the-shelf Python decompiler, and you should be able to basically unpack the installer that you download from their webpage, and you can just decompile the whole application. And then you have some very nice readable Python. There's like a whole lot of files that you have to look at here. A lot of these are not really needed for the core application, but there's still like a lot of filtering about what is actually relevant, what is not. It communicates over TLS, which is of course like needed to not be like really broken, I suppose. It does mean that of course like man-in-the-middle type attacks are not possible. We don't really care about this because in the end we want to protect against the server, and the server is like the intended recipient of your data in any event. So TLS doesn't really factor into this whole like attack scenario we envision here. In practice, of course, you still want to have TLS because otherwise, like, everybody can just read what you have. Or I guess you could say it as like, if the application is broken and you're not using TLS, then it's not broken only towards the server, it's basically broken towards the whole world, which is like somewhat more bad, I guess, somewhat better. It does make experimenting a bit difficult because it has like hard-coded certificates and so on. So, and also like analyzing what traffic it sends back and forth also became like sort of difficult. The approach we took is I guess you could say like the tried and true test of like debugging by printing. You know, when you write a program, you put like print statements everywhere to see what's actually going on. We do the same thing because now we could decompile the whole thing, and then we made use of the logging framework that it already had to print stuff all over the place in the application. And we did this, for example, to print the connection keys that it uses in the TLS. So it prints this, and now we can capture all the traffic in Wireshark, and then we can load these keys into Wireshark afterwards, and now we can actually read what it's sending back and forth without actually touching the application, except for like very minimally in some places. Okay, so the attacks, I guess, the interesting part, the fun part. We found 4 different things. So one of them is basically you could, again, this thing where you compute some deviation of the user's password in connection to some authentication. Like basically it's possible to weaken this to a point where it most likely doesn't provide like adequate security anymore. Like it doesn't hide the password well enough, essentially. We found 2 attacks that can recover the user's password. One somehow requires some interaction from the user that you might say, okay, this is not realistic, or it is realistic. And if you don't believe that one, we also found one that does the same thing, but like now it doesn't require any interaction from the user at all. So like it can just happen silently in the background while the user does absolutely nothing. And then we found an interesting attack which actually reveals files also without the user doing anything, but this is actually also happens without the server doing anything. So this is essentially like certain use patterns of this application, or like of this feature, which is like file sharing in this case, will actually reveal more than it's supposed to. So essentially you say, I share this file, but now you inadvertently also share like 2 other files, basically. Something like this has happened. Yes, of course, like the required statement, we contacted them and they fixed it, and we did this before we made anything public, and so on and so forth, of course. So the first one, like the uninteresting one, because it basically just, if you have a good password, then this doesn't matter. If you have a bad password, then likely this doesn't matter either, because like usually you have a very terrible password, or you have a password that is like good enough. You don't have a password that is like only slightly good enough. If you hash it like twice more, then it's suddenly good or something. Right? That's not how passwords work. But in any event, one of these authentication protocols that it uses is basically password over TLS, but now the hashing that you usually perform on the server side as part of this authentication protocol, now it happens on the client side as well. So like this is the easiest way perhaps to avoid the problem of sending your password to the server. So this is essentially what happens. So the server will send some random number, random string to the client. The client computes a derivation using, in this case, bcrypt, which is it's an iterated hash function essentially. All right, it's like it's a hash function you apply on itself, and then just do this a lot of times. So now it's expensive to compute, and this provides a bit more security to just doing it once, for example. That's essentially how it works. It uses a block cipher, but it's the same thing. So you send this back, and the server will say, oh, you know, you're the person you claim to be if this matches some hash that it already has on the server, right? The problem is that in bcrypt, the salt contains essentially everything that the client needs in order to compute the function. In particular, it also includes the parameters for how expensive this function should be. So instead of saying that this should be 12, which is like the default on almost all libraries and machines and recommendations, which is like 2 to the 12 iterations, which is some power of 2. I can't calculate in my head right now, of course. You can basically take and like just push this all the way down until the library the library they're using starts complaining that this is, you know, below what it's supposed to do. In practice, you could put this down to 4, which is now 16. So 16 iterations of this underlying function, which is like very, very fast. This is of course not enough. This is like way less than is recommended in the original bcrypt paper from '92. So of course it's also not enough in 2017 or 18 or 19. it's a factor 8 downgrade. In principle, this is essentially getting like an MD5, like in terms of computation required and so on, it's essentially getting an MD5 of the user's password, something like this, which is not enough in practice. But this, of course, doesn't reveal anything. It just makes it easier for already weak passwords to be broken, basically. So the first password recovery. So again, this is again an attack on one of these authentication protocols. Interestingly, they had 4 authentication protocols that we discovered in the application. So the way it authenticates is, or the way it runs these protocols is the server tells the client, please run this protocol, and now they run a protocol and stuff happens. There's like 4 of these in the application, and it only ever used 2 of them when we looked at how it operated when you just use it normally. But of course, if we assume the server just does whatever it wants, it can just tell the client to run, one of these protocols that might be not used anymore, for example, or might be used for different things. In this case, it's not used in the client server setting. It's used in most likely something else, in like an key escrow setting, which is basically what this does. Anyways, so how this works is that the server can say, run this protocol, and here is a list of RSA keys, and here is a random number. Okay? So now the client, first it does something. It computes like a function of this list. It computes a fingerprint using some RFC that is also from the late 90s. It tells you how to take a binary string, then chop it into pieces, and then map these pieces to English words, and then how to display this string as a list of English words, basically. So what it does, so that's basically what it does. It hashes the fingerprint, it hashes this list of keys. It uses this thing to convert it into a string of numbers. It displays these to the user, and the user is asked, do I trust this random, like this string of random numbers? If yes, click, continue. If no, click cancel. If the user clicks continue, then you use these keys to basically encrypt a concatenation of the password in the challenge, and then just like iterate it. And now you send this back to the server. Of course, the attack here is clear if we ignore this fingerprinty thing for a moment, is that the server just picks its own keys, right? So he picks some keys, he asks the user to encrypt what is basically his password in this challenge under keys that he knows how to decrypt. And of course, this learns, this reveals the password to the server. As a small aside, we also found that if this list is empty, the user will the client will just send back this thing, like unencrypted also. So you don't actually even need to have the keys. You can just send nothing, and then you just get back the password. So it saves a bit of work on the server, I guess. Yeah, of course, this is what's it. So, but when we change this list, yeah, so you get these this string of random words that the user have to accept. So the question is how realistic is it that a user will accept it? And in this case, we argue that it's very realistic because together with this list of words, you also get this nice warning, which says something about this fingerprint phrase, and it also says that if you have not been giving this fingerprint before, then just click yes anyway. Which is, you can sort of compare this to a certificate you get when you visit a web page, right? And obviously, if your browser says, I don't trust the certificate, it shouldn't be, I have not seen this certificate before, so just click yes. Which is probably what most users do anyway, but it shouldn't be encouraged by the application at least. They fixed this by, not really fixing this protocol because we believe they use it for their enterprise products because it does provide a form of escrowing encryption keys and passwords. But they fixed this wording. So now it doesn't say that you should just ignore, common logic and just accept whatever it's trusted. But it is a proper thing in software, right? It's trust on first use in this case. Yes, so file recovery, I'll take this. This is the one I mentioned where it's basically like a use pattern that ends up breaking the application or the security of some of your files in some sense. The server actually doesn't have to do anything in this case. So it's based on how this encryption works. So if you share a directory, this happens by revealing this directory key. So you encrypt the file with a directory key, and these keys are encrypted with your password essentially. But now if all the files in a specific directory is encrypted with the same key, if you just reveal this directory key, the server can actually recover all the like individual file keys and now all the individual files. So that's how it works. The problem is that when you start moving files around in like a directory on your computer, this is not really reflected in these keys. So in like there's no like re-encryption of these keys. So somehow like there's a mismatch in like the view the application have of your directories and the view that you have of your directories. And yeah, these directory keys are never rotated. So it's quite easy to come up with like scenarios where this is bad. So for example, if you have a directory with some files, you move one of them to a different directory and then you share the old one. Now, because of these things up here, I mentioned here, when you move this to a different directory, the encryption of this guy is not updated. So it's actually still secured under whatever key is associated with this old directory. And now you share the old directory, this also reveals the file you moved away, right? So like this is, and it's quite easy to think of like scenarios in real life where this applies, right? It's like this is all your vacation photos, and this is like a particularly not shareable vacation photo, right? You move it to a private folder and then you share your vacation photos, but now the server has all your vacation photos, right? Obviously you don't want this to happen. The sort of like reverse also happens. If you have a directory with like shared files, say this from before, you can like keep adding stuff to it. It will be encrypted under a key that the server already knows. So now it's also like intuitively shared when you do this. If you stop sharing this directory, because these directory keys are not updated, when you now add new files to a directory that is no longer supposed to be shared, it's still going to be encrypted using a key that the server knows, right? So this also provides some sort of like false sense of security essentially for a directory that you don't think is shared, but it's actually shared because it happened to be shared somehow in the past. And I guess like these two situations in particular can be bad, right? If you use this application for a long time, you like keep adding directories, you keep moving stuff around and so on. Like at some point, like who knows what is actually known by the server and which is not, right? Okay, so a bit of time, I guess. Both. I guess this is worth stressing that in both of these cases, you actually take specific actions, right? In this case, in step 2 here, in this case, also step 2, like the user actually takes like specific actions to avoid sharing files in this case. But somehow like security, like the privacy of his files are still like not there. Okay. So finally, the completely silent password recovery doesn't use that protocols are broken. It just uses, I guess, dead code and bad programming, I suppose. Anyways, after installation, in order to like authenticate automatically, basically, when you start up your application after you boot and so on, this happens because the password is basically stored in plain text on your own computer. It also means that if you're using SpiderOak, most likely you shouldn't lose your computer because if somebody gets access to the files in this computer, they actually also get access to the password that you're using, even if it was like turned off. At least if they're still doing what they're doing here, which I think they are. But they store the user's password in clear text, plain text, on the user's machine, because this means you don't have to input it to the application every time it starts, because now it can just run whatever authentication protocol it's supposed to run with the server, just runs it normally, like automatically, right? We found some like RPC methods that most likely have to do with like debugging and so on, which is like you can give it a file path and then it returns the content of this file. So now you might imagine like what the attack here might be, right? It's that we could like it accepted the file, like the path for the file containing the user's password as for this method. So basically the server can tell the user, or the client can tell it, please send me the content of this file, I need it for debugging. And now the client will just send back this file that already contains the user's password in clear text. Which is like, yeah, the check here is, it's not sufficient to guard against this attack. So it's like there's all of these like interesting protocols they write and so on, and then in the end, like the most broken part of this is just like, I don't know, old code. the fix they had for this one was just to remove these methods because they were not used according to them. So yeah, I guess. Yeah, so some conclusions, like I'm a bit ahead of time, I think, but okay. Yeah, like I have one slide left, so. Some takeaways, I think. So it's not just attacks. The main interesting part is authentication. Like authentication in this case is the reason for all of the attacks except the one with the file sharing and moving stuff around and so on. But the fact that they have to come up with like their own authentication protocols in order to get around the fact that you have to send the password and so on just breaks everything. And it's in particularly bad in this case because the password that you enter in order to say I'm whoever I claim to be is also the password that you use to encrypt your files. So now if they write like a broken authentication protocol, which they did at least twice here, you also break like the security of the confidentiality of your files, basically. The application is somewhat over-permissive in these RPC methods. And this also ties somehow into the threat model that we used. It's like in the end, it's not clear like what exactly is the trust, like the threat model that they're using. They claim to, you know, oh, you shouldn't be able to trust us. But of course, this is somehow, at least if you care about it, it's not really that, it doesn't tell you much about like the actual security. So the application is somewhat overly permissive in how much the server is allowed to do. Is this an issue? Maybe depends on how much you trust the server, trust this application. If the application designers are like upfront at the beginning saying like this is the specific threat model that we use, then it's easier to say that okay, this matches my expectations of security from this product. Or if it doesn't, then you just don't use it, instead of this thing where you think that, you know, the claim they have on their front page is like, oh, it means that, you know, regardless of what happens, my files are still secure, which is not the case here. Well, the security provider should match the claims. I think that's like an obvious one. Of course, somehow formalizing the security provided in a way that makes it, you know, somehow equivalent to these nice claims they have on the front page is hardly a trivial thing to do. It's like, it's a very non-trivial thing to do, actually. But there should be at least more than just this pitch, sales pitch, so to speak, I think. And yeah, if they use like custom-made protocols, they should be possible to audit these protocols. Like in this case, it's easy or easy-ish to audit the protocols because, like, in the end, the application was written in Python, so that like took that removed like a large requirement of having to debug this program. But if you want to like audit some of these other applications that also does encryption and so on, and then the only thing you have to work with is like a compiled C++ program or something, then it's like suddenly this is a lot harder to do, of course, right? So it should be possible. They should at least like describe how this protocol works. As I don't think there's any case of anything in the history of software where anybody has, well, I was going to be, has gained anything by like designing their own protocol and somehow basing security partly or in total on this protocol somehow being hidden from everybody else. Like, it doesn't work. It doesn't work in cryptography, and I doubt that it works in protocol design as well. So that's it, basically. So, questions? Yes.
Thank you for the talk. That was interesting. Am I understanding correctly that the sharing feature actually isn't meant to be end-to-end encrypted? You
Yes.
normally just reveal the content of the...
Yep, you just reveal, in this application, you just reveal the content to the server.
Is that, I mean, obviously, like, there are things that have end-to-end file sharing where, like, for all their talk about zero knowledge, I'm very surprised to learn that that's the intended design of it. I wonder, do you think they make that clear to users at all? I've never actually used this software, but I've seen it advertised, and this seems totally counter to their...
Yes, so like it's very strange, this file sharing thingy, where you just reveal stuff. Partly one of the reasons we wanted to look at this particular piece of software in the beginning is, they have it here, is that this thing they call no knowledge.
Yeah, which is totally
Used to be called zero knowledge at some point, which means a total different thing if you study cryptography. So that was like a large red flag in the beginning. It's like, oh, they use this word, and I don't think they know what it means. But yeah, they don't for the file sharing. No, they don't. It's different from, for example, something like mega upload, where the key is actually like the whole thing happens in your browser. So now it's actually proper end-to-end encrypted also for like sharing of files.
Yeah.
It's not revealed to the client, but not in this case. No, in this case, it's just you reveal this content to the server, and now the server acts as essentially like a normal file sharing system.
But is that like clear in the user interface? Like when you install the software and use it, do you think most users who are paying for SpiderOak are...
For file sharing, I think so. I seem to remember that this is like they mentioned this. They have like a bunch of caveats also. Like if you log into their log into your account on their website, they also have like a small footnote saying now it doesn't apply anymore, this file sharing, because you log in with your password, and this is normal password over TLS when you log into their website.
Yeah.
It's just like, so yeah.
So when they fixed this bug door RPC method for asking the client for the password, did they do an advisory about that?
No. They wrote a blog post, which I think is now, it might be lost now because they redesigned their webpage. So now conveniently they lost a lot of stuff.
Was it written about in the media at all? Like was there any press?
It was in the, I was interviewed for an article for version 2, like version 2, like a Danish thing. So.
All right. Well, thank you for the research and the talk.
Yeah.
Any other questions? No? Then let's give Anders a big hand.